So how we can use Reynolds number for the pipe flow? Right, so for pipe flow, Reynolds number is used to determine the nature of flow. So when the pipe is smooth, right, smooth pipe, so Reynolds number should be less than 2100, right? So let's say you want to know at what maximum average velocity in the pipe that the flow is laminar. So rho V D divided by mu. Let's say our fluid, right? Let's say we have unknown fluid. The dynamic viscosity is 1 times 10 to minus 3 Pascal second, right? Let's say we don't know this fluid, and then the density is 1000 kilogram per meter cube, right? This assumption that we made. And then what else? The pipe have a diameter. Diameter, let's say, is 25 mm. So 25 times 10 minus 3 meter. Right, so we have to convert our apa ni, everything is in proper unit. Everything should be, if meter, you have to use all meters, right? So we want to find what is the values of average velocity in the pipe, and then the pipe is considered laminar flow, right? We know the nature of the pipe flow when the flow is laminar. Let's say we look again the experiment by Reynolds, right? Osborne Reynolds. So it has a tank, and then there is a pipe, and then it is a die. Let's say put a die here, right? A die there, and this die, if the tube connecting the die is stationary, right? So this is the tube, and we put some die there. Because of the weight of the die, it will flow down, and it will produce a fine streak of fluid flow, right, of the die flow. So you can see the line. So and then it start to make a transition to turbulent flow. So we want to know what is the velocity at that particular region, right? So we want to know what is the velocity there. So these are the actual values. We want to know the average velocity distribution, right? So this is the average velocity distribution that we expect from the fluid. So what we need to do is to use our ni. Let me use my calculators. That. So we have the Reynolds number. If we rearrange the equation, V average equal to Reynolds number time dynamic viscosity divided by density multiplied with the diameter. So we have 2100 times the dynamic viscosity 1 divided by 1000, and then we divide with the density 1000, and then multiply with the diameters. Diameters is 25 mm, divide 1000. Right, so we have the average velocity is 0.084 meter per second. Let's say we have a clock, right? And the clock is from 0 to 1 second. Let's say 1 second. This is our clock. We have resolution maybe 0.1 second, 0.5 4 second, 0.8 second, and finally at 1 second. So we have a fluid particle which is moved at 0.084, right? 84 millimeter per second. So when it reaches to 1 second, let's say I have a ruler here, 84. Where is 84? Right, so up to here. So it takes a length of 84 millimeters. In 1 second. So this is what it mean by this average value. So at all position, right? At all position, so this one will be 84 mm millimeter dia punya vectors. We have Reynolds number greater than 2100. Mana tadi? 2100. So it means that the fluid is greater than that. So the fluid become turbulent, right? So we expect that the fluid flow inside the tubes, inside the pipe, will be not having a irregular shape. Now, can we make the flow to become turbulent at lower speed? It's possible to do that. There are various factors. For example, the pipe is not smooth, right? You have a very rough pipe. This is because of the manufacturing process, so the pipe become rough. Or if the pipe is corroded, for example, so the fluid will become turbulent. You have a very low Reynolds number. If we have a very good shining smooth pipe, right? So we can extend this one further. But this is the only specific for smooth pipe. So you cannot use for other geometry.